In this session, we will learn how to compute linear prediction coefficients. Linear prediction analysis needs to determine alpha k directly from speech such that they give good estimates of the time varying spectrum of the speech. It needs to estimate alpha k from short segments of speech and needs to minimize mean squared prediction error over short segments of speech. This is one commonly used criterion named MMSE. By means of MMSE, LP coefficients can be adjusted and selected to make the prediction error the least. The resulting linear prediction coefficients, alpha k, are assumed to be the actual AK in the speech production model, intending to show that all of the processing can be done efficiently, reliably, and accurately for speech. How to compute linear prediction coefficients, alpha k? Firstly, we define the short-time average prediction squared error as En. We can compute En by selecting segment of speech in the vicinity of sample n. The key issue to resolve is the range of m for summation. Different selection of the range m leads to different kind of algorithms which will be mentioned later. We can minimize the prediction square error En using the form of partial derivative. Then the set of equations can be given to compute the estimated LP coefficients, alpha hat. As is shown in the equations, prediction error ENM is orthogonal to the signal SNM. For delays Si of the order 1 to p. By defining another function, phi n, we can get a set of p equations in p unknowns that can be solved in an efficient manner for the alpha k. The original form of minimum mean squared prediction error can be written in another form with function phi n by computing phi n and solving the metric equations. We can get the prediction coefficients alpha k. The range of m needs to be specified to compute phi n. The input speech segment SNM should also be specified. There are two typical methods to compute the linear predictions coefficients. One is autocorrelation method, which assumes that SNM exists for the range 0 to L minus 1, I'm greater than or equal to 0, less than or equal to L minus 1, and exactly 0 everywhere else. That is to say, the window Wm is a finite length window of L samples. Because SNM is equal to 0 outside the range from 0 to L minus 1, m greater than or equal to 0, less than or equal to L minus 1. Then the matrix equation phi n could be expressed in another form. There are some non-zero terms in the computation of phi ik for each value of I and k. The equation can be easily expressed with the short-time autocorrelation function Rnk of Sm evaluated at I minus k. Since Rnk is even, then the basic equations with phi n could be expressed with the form of autocorrelation function. According to the new expression of phi n, we can rewrite the minimum mean squared prediction error En with the short-time autocorrelation function Rnk. That is why we call the method autocorrelation method. By using this method, we just need to solve the equations in matrix form to get the linear prediction coefficients alpha k. The matrix phi n ik is shown to be an autocorrelation function. The resulting autocorrelation matrix is P times P Topliss matrix, which is symmetric with all diagonal elements equal. It can be readily solved using standard matrix solutions. As to the Topliss matrix, the solution of the I-order equation system can be represented by the solution of the I-1 order equation system. The solution of the I-1 order equation system can be represented by the solution of the I-2 order equation system, and so on. Thus, as long as the first order of equation system is solved, the other equations of any order can be recursively solved. There are two typical algorithms, including Levin-Dubin recursion and Schur recursion. The figure shows the computation process of autocorrelation method. Signal is windowed by a tapering window, for example, Hamming window, in order to minimize discontinuities at the beginning and end of the interval. At the beginning, speech is predicted from zero-valued samples. At the end, zero-valued samples are predicted from speech samples. In the autocorrelation method, the input signal SNM is defined for the range m from 0 to L-1, m which is greater than or equal to 0, less than or equal to L-1. The prediction error ENM is also defined for the range m from 0 to L-1 plus p. Large errors can be found for the ranges with m from 0 to p-1 and m from L to L-1 plus p. We can see from the figure that large errors occur at the ends of window. There is a second basic approach to define the speech segment SNM, and the limits on the sums, namely to fix the interval over which the mean square error is computed. By changing the summation index, we can get another form of covariance function, phi n ik. Such kind of method is called covariance method. The key difference of covariance method from autocorrelation method is that the limits of summation include terms before m equals 0. Thus, the window extends p samples backwards from xn minus p to xm plus L minus 1. Since we extend the window backwards, we don't need to taper it using a Hamming window, because there is no transition at window edges. In covariance method, the signal is extended by p samples outside the normal range of m from 0 to L-1, which is greater than or equal to minus p, less than or equal to L-1, in order to include p samples occurring prior to m equals 0. This eliminates the large errors in computing the signal from values prior to m equals 0, and eliminates the need for a tapering window. The figure shows the computation process of covariance method. Signal is windowed without tapering window and extended by P samples. At the beginning, speech is predicted from the past P samples. Courier's method leads to much smaller prediction error than autocorrelation method. This method has a true cross-correlation, thus cannot use autocorrelation formulation. It needs to solve set of equations of another form with Courier's function phi n ik. Resulting matrix of correlations phi n ik is symmetric but not topless. All terms of phi n ik have a fixed number of terms, L terms, contributing to the computed values. Because phi n ik is a covariance matrix, specialized solution for alpha k is called the covariance method. Let's have a summary of linear prediction. Linear prediction model can approximately describe the speech production model. It uses pth order linear predictor to predict Sn from P previous samples over analysis window of duration L samples. Linear prediction parameters can be gotten by the method of linear minimization using mean square error criterion. Solution for optimum predictor coefficients alpha k is based on solving a metric equation. Different methods of solution lead to somewhat different set of optimal prediction coefficients. The commonly used methods are autocorrelation method and the covariance method. The two methods compute signal in different range of interval and lead to different types of metric equation solution. That's all for this session. See you next session.